the camera is like up here, but I have it.
So the whole area here is covered. So
Okay, and at the moment the slides aren't very visible, but
It's
always like that,
yeah. Pick it up very well.
yeah, you can
It's for
share
people
it.
who just can't be in Pittsburgh.
Yeah, no, that's okay.
and then check this one.
This is working.
That's working.
Yeah, that's
But
working.
if you feel like it's too
But
small,
is this red spot bigger here? Oh, yeah.
I wonder. I looked
it's not working.
Oh, I think it's the same size. If you, well, it's brighter. So this one is brighter. I don't know. I think I'll be using this one just to make sure.
And I'll come get the mic from you all before the Q&A.
Very good. So yeah. So I've been wiretapped. So we can't have a conversation now. Hey.
All right, so let's get started. Before introducing today's speakers, I wanted to make a few announcements. There is no lunch talk on Friday because there is the annual lecture series talk given by Andrea Woody at 3:30 on the 10th floor. And the topic of Andrea's talk is going to be smart search through complex landscapes, unification as a methodological strategy. On Tuesday next week, Zed Adams is going to be giving a talk on the history and philosophical significance of the analog-digital distinction here at the center at noon. And on Friday next week, on Friday and Saturday next week, there will be the conference on organized by the senior visiting fellow Bill Wimsatt on returning cognition with a pair of rocks, culture, evolution, technology. Here at the center, it's a wonderful conference. Please have a look at the program online. And if you're interested in the conference, please register online for the conference so that we know how many people are going to be coming. Today, it's my great pleasure to introduce two friends of the center and of Pete more broadly. Tomasz Placek and Tomasz Müller, who are here, who are going to be talking about the following topic: quantum correlation analyzed modally in the branching space-time framework. Tomasz Placek is a professor at the Institute of Philosophy at, I'm afraid I'm going to butcher the name, Jagiellonian University.
Close enough. American pronunciation, very good.
And I'm not sure that was very sincere, but who is coming from Krakow in Poland. So Tomasz worked in the philosophy of physics, metaphysics, also with interest in HPS as well as philosophical logic, as we've seen today. He's been a fellow of the center in 2004, so some time ago, and also has worked extensively here with Noel Belknap. And Tomasz Müller all comes from the University of Constance and works on the same area, philosophy of physics, metaphysics, philosophy of science, as well as logic, and is professor there. So welcome, and also he's been at the University of Pittsburgh many times. So welcome back, and the floor is yours.
Okay. Thanks very much for coming. Thanks very much for having us here. It's a great pleasure to be back in Pittsburgh and to be presenting here. And it's a great pleasure that Noel Belknap, about whose work this is more or less, is also present in the audience. So welcome, Noel. We're going to share this talk between the two of us. So I'll go first. And then the interesting stuff is Tomasz. He will give the example. But I'll try to give a broad intro. and lead you through some formal constructions that will then be used, that will be necessary for the example. So does 2 times 2 make 2, or does 2 times 2 make 4, right? That's a big question, and the answer is obvious. It depends, right? So here's a picture that many of you will have seen, which illustrates quantum correlations for entangled particle pairs, right? So it's an empirical fact, it seems, very well established, that there can be situations in which you have the following. There is a pair of particles. You divide the pair up into 2 parts. They fly apart. And then at certain points, at space-like distance from each other, you do an experiment on the one particle, and you do an experiment on the other particle, and each of those experiments can give one of 2 outcomes. Let's say plus or minus, spin up or spin down, for the standard example of the Bohm EPR experiment, as it's called. So that's fine. 2 possibilities here, 2 possibilities here, right? But it turns out that overall, there's only 2 joint possibilities, where by space-like separation, you would think what happens here has got to be independent from what happens here. So there should be 4 possibilities jointly, right? And now this is, of course, a simplification. If you do the experiments, you have to do a probabilistic analysis. And so as a disclaimer to all of what I'm going to say today, we will exclusively focus on the modal structure, so on the structure of possibilities and impossibilities, and we will disregard probabilities. We think that it's still interesting to look at these modal correlations, and the example that Tomasz will be talking about, which is an extension of this scheme known to many of you, I guess, under the name of GHZ, Greenberger, Horn, Zeilinger, an extension of a 3-particle system where the correlations are truly modal and not just probabilistic. So what we'll be looking at generally is possibilities that are local in space and time, the way these possibilities combine or fail to combine, and strategies for understanding what is going on and how they fail. So here's the setup. I'll start by embedding what we are going to present today in a larger project, which I think was started around 30 years ago in Pittsburgh by Müller. And I'll say a little bit about this project and how what we are doing today fits into the overall project. And then I'll talk about this case of modal correlations. I'll introduce it in somewhat more detail, at first at a informal level, and then I'll give some formal details. And then I'll hand over to Tomasz, who will walk you through an application of our framework for this Greenberger, Horn, Zeilinger setup, and we'll have a brief conclusion. So here's the overall project. There is an article that appeared in 1992 in the journal Synthese, and its first sentence is this: how can we combine relativity and indeterminism in a rigorous theory? So why is that interesting? Talking with Müller, I learned that the primary motivation for coming up with this theory is in connection with an account of agency, right? So suppose someone does something here and someone else does something over there, and they haven't agreed on what to do jointly, then whatever someone does here and whatever the other person does over there, it's going to be independent, right? That's an assumption we make. And it's an assumption that you have to enter into a formal theory of agency as an explicit, let's say, independence of joint actions axiom. And the hope is that by exploiting the resources of space-time theory, which gives you a notion of space-like separation providing for causal independence, you can get rid of the necessity of that axiom for the possibility or the independence of joint action just from the space-time background. So that's the agency-related idea. If you have a local possibility due to an agent here, and a local possibility due to another agent over there, then whatever this guy does and whatever this guy does, it's going to be independent. So all possibilities should, all joint possibilities should be global possibilities for the pair of agents, right? And extending that to many, many agents. But there's, of course, also an interest in coming up with a theory that shows how to combine indeterminism and relativity theory from a philosophy of science perspective. And quantum correlations are one application for it along that line, and that's what we'll be talking about today. Overall, looking at the project from a metaphysical point of view, it provides you with a perspective of modality that takes modalities to be basic for the theory. So they're represented as basic objects and not derived in some roundabout way. So it's a non-Humean approach. What we're currently working on, Tomasz and I with Müller together, we're working on a book really, and it's going to provide a unified approach to this branching spacetimes theory. Because over the years, the theory was developed in many different articles, many separate publications, and we want to unify it and have some applications. So the application today is from the book project, really. So the idea of coming up with branching spacetimes is in this commuting diagram. You start with a Newtonian idea that there is space and there is time, and they're, as it were, orthogonal to each other. So you have a global now throughout all of space, and you stack all these nows, and that gives you space times time. You can have a theory of indeterminism that's built on this Newtonian framework by moving from the idea of time as linear to an idea where you allow for a branching tree of histories, of possibilities that branch off in the future. And you can also move from the Newtonian idea of space and time as separate to the notion of space-time as, for example, in special relativity. Now, if you combine these two moves away from Newtonian space and time, you arrive at the theory of branching spacetimes. I'll not go over all the formal details. The important idea is you combine possibilities that are localized in space-time in such a way that you arrive at a unified framework in which you have the different possible courses of events, total courses of events, as branching histories. So a history in this framework, a total possible course of events, will be something like a space-time, right? And you will have many of these space-times that overlap at certain regions and that fail to overlap in inconsistent future possibilities. Okay, so now modal funny business. So there is a formally well-defined notion of modal funny business that comes from work of Müller in the early 2000s. The idea of modal funny business is that sometimes, as I said in my intro slide, local possibilities will not combine smoothly to form global possibilities, right? And I will write a local possibility in the following way. And that's now important. So you will see later on diagrams where this is like just a frame, and you will have a point, let's say E. This will be a point event as known from relativity theory. So it has a future light cone, right? And now let's suppose above E, immediately above E, there could be one outcome, let's say plus, or immediately above E, there could be a different outcome, let's say minus. Then we're going to write, so let's say we call this a history 1, and this would be a history 2. And then we will be able to talk about this local possibility in what is called a transition from E, which is the initial of the transition, to one of the immediate outcomes of E, which in this case will be only one history, namely H1, right? So there are two histories that pass through this event E, both histories, right? H1 and H2. So in the formal structure, they both contain the same element, E, these two histories, but they split at this point E, and the splitting is locally accounted for by these so-called transitions. That's really the basic formal framework that we're going to be working with. So now there's a question, right? Suppose I give you a bunch of local possibilities. Will they combine to form a global possibility? And you might think, well, if they're local, then in a way they should be independent. And so maybe they always have to have a global possibility. But when you think again, of course, that's not so. Sometimes you have local possibilities about which you expect that they won't combine to form a global possibility. And when that's so, it's boring. But when that's not so, then you have an interesting case, and that will be modal funny business. I'd rather give you informal illustrations now than walk through the formal definition. So here is one boring case, right? So I toss a coin. The coin can come up heads, and it can come up tails. So there's one local possibility. Coin toss heads, coin toss tails. Now, what about those two local possibilities combined? Can they happen? Well, of course not, right? Because they're local alternatives. They're alternatives to the same initial. So that is something we call blatant inconsistency, right? So whenever you run together two local possibilities that from the same initial, then they have to be incompatible. Here's another boring case. Suppose in the morning I can have orange juice or I can have coffee. If I have coffee, I can have it black or I can take milk. So the space-time picture will be like this. So this is the orange juice history, right? And then if I have coffee, I will say, I will have the possibility of choosing to have my coffee black, but I will always also have the possibility of choosing to have my coffee with milk, right? So now I have two local possibilities from the initial choice to orange juice and from coffee with milk, with or without milk, to having my coffee black. And they are local possibilities, but they don't combine smoothly to form a global possibility, even though they don't contain the same initial choice event, right? And why is that? Well, if you look at the situation, then of course you see that in order for you to be facing this choice of having your coffee black or with milk, you have to have selected the coffee and not the orange juice. So in a way, the occurrence of this event implies the occurrence of the past transition, which is incompatible with this one. So in a way, this does come down to blatant inconsistency in a suitable extension. So we can write these, let's call this guy E2 and this one E1. So you will have this situation. There is an initial E1 that has two possible outcomes. And in one of those outcomes, you have another initial. Then, of course, for this local possibility to occur, this local possibility has got to have been realized. So this local possibility and this one, they are also inconsistent, right? And I mean, this sounds trivial, and in a sense it is, but this is behind a lot of trouble with propensity theory. So this is just a side remark, but if you look at Humphrey's argument against propensities, then what is happening is people take these local spaces and they do a Cartesian product construction, and then some problem occurs, whereas the real way of combining local possibilities gives you not 4 but 3 options here. So we can talk about that if you like later. So here is again our interesting case of local possibilities not combining smoothly, strange modal correlations. So in this experiment, as I said, there are these 2 local possibilities and they're space-like separated, and the initials can occur together, right? They're friendly, they occur in the same situation, but from among these local possibilities, you would expect 4 global possibilities, and not all 4 of them are realized. And that's what we call modal funny business, right? It's formally well defined in Newell's papers and in some later papers. Okay, so now if you're faced with modal funny business, what are you going to do, right? And we have the slogan, correlations cry out for explanation. So the idea is, and this is basically what happens in the famous EPR paper from Einstein, Podolsky and Rosen 1935, right? There is a troublesome surface modal correlation, and you think this must be due to an incompleteness of your description. So if you complete the description, there is an underlying hidden structure that explains away these troublesome correlations. And the formal idea is now you take the initial setup, right? So this one, and you say, yo, but look, in the past of these initials, there's got to be something that tells you whether you're going to land up in this situation or in that situation. So the basic idea is really you take a surface model that has these modal correlations, you try to complement it with some additional structure in the past such that the correlations disappear. And formally what you do is you introduce a new splitting in the past, and you delete splittings in the from the initials, right? So in this EPR case, it would be very simple. You would just say, oh, there were those 2 plus minus splittings. What is really going on, you're now saying, is that here there is another point, let's call it, so this is, let's say, E1 and E2, and they together form a set E. And what is really happening is that this E star point, as it were, already contains the full splitting, and what is happening here is just, as it were, reading out what was already predetermined at E star, right? So this is all standard, and this is all in a way maybe boring, but I think that our framework can point out an important feature of all the interesting cases of modal correlations that are easy to talk over if you don't do a formal construction. And that's what we think the value of our work might be. So it's this, I mean, what I just illustrated is, if you're going to introduce a new point, a new splitting E star, such that all the indeterminism above is accounted for at E star, then of course you will be able to do away with all correlations above there, right? So let's suppose E1 plus and E2 plus, they're impossible. Well, then at E star you will just write down instructions that allow only for plus minus, let's say, and minus plus. And you will not allow at E star for instructions to be provided to have plus plus here. So if all the indeterminism above is, as it were, gobbled up by what happens at E star, then you can remove any kind of correlations. But now, in all interesting, I think really in all interesting modal correlation setups, and I think this extends to the probabilistic case, but as I said, we're only doing the modal case here. In all interesting setups, you have the following. there are two types of indeterminism involved. There is one type of indeterminism which is, as it were, due to nature, so what your entangled pair of particles is doing, let's say. And there is one type of indeterminism or choice or exogenous influence or whatever you want to call it, that is due to an experimenter making a certain selection. And unless such a setup includes such selection events, it will be uninteresting to complement it with hidden variables. You will always be able to do it and there will be no problem. Whereas in the literature, and this is often not in the center of the formal derivations, but in the literature, when you end up accounting for the experimenter's choices also at this point E star, right? Then people will accuse you of, or they will at least describe what you're doing as introducing a super deterministic complementation. Or they will accuse you of introducing a conspiracy. Because the idea is you want to account for what nature is doing here, but you want to leave the experimenter free to select whatever, let's say, measurement arrangement they want to come up with. And this is already present in the original EPR paper, this kind of structure. So it will always look like this. Let's see. So let's say there is a possibility of having, let's now call this x1 and then x2, but I could also be doing, let's say, y1, a different experiment on my first particle, and x2, and there will have to be an experimenter's choice. Let's just write this 1. So experimenter 1 gets to select which of these experiments is done, the X experiment or the Y experiment, right? And what you want to do with your E star introduction is to account for any correlations here, but not to delete the choice nature of what happens on the experimenter's side. Right? That's really, I think, the general thrust of these complementations. So the complementations are not just to remove the correlations. The challenge is to come up with a complementation that removes the correlations while keeping the experimenter's choice intact. So I'm sort of running behind schedule. So this is more or less what I've said. There are two ways to do this, and I think the following is more or less fair to what is used as a terminology, even though people don't talk about the modal case very much. So suppose two experimenters get to make a choice, right? Then at E star, so let's say we're now looking at x1 versus y1 selected by this one person, and x2 versus y2 selected by the other person. And now you want E star to give instructions for what is to happen at x1, x2, y1, and y2. And you can do this in two ways, and it gets harder as the non-contextual is harder than the contextual. So the non-contextual way would be to say E star gives instructions for whatever 1 and 2 may choose independently. So an instruction set at E star in the non-contextual setting will look like this. It will say what has to happen at x1, let's say plus, what has to happen at x2, let's say minus, what has to happen at y1, let's say plus, and what's going to happen at y2, let's say minus, right? So this will be an instruction set that is non-contextual in the sense that no matter what one or two come up with through their choice of initials, you can use this instruction set to uniformly provide outcomes for x and y. So you'll have a splitting down here that leaves it open for 1 and 2 to select whatever they want, and then x1, y2, whatever, they will read out what they have to come up with, and you will get a surface model, right? And one question is, can you always do that? And the answer is no. So there is another possibility of providing instruction sets which is different. Namely, it says, oh, if the one guy selects X, then I'm going plus, and if the other guy, so if the one guy, sorry, I have to write it like this. So if the one guy selects X and the two guys selects Y, then I'm going to do plus plus. Whereas if the one guy selects X and the two guys selects Y, then let's say I'm going to do minus plus. And so forth. So there will be 4 of those, right? And that gives you more information and thereby more freedom. And the question is this going to be helpful or is this going to be interesting? So I think I'll just flash the formal definitions of what these 2 ways of providing instruction set at E star, what they look like, and then I'm handing over to Tomasz to run you through a concrete example. So there is some hand scratches here, as Noel says, some formalism, but bear with me. So we have the general setup, which is this. So there is our position of the initial E star, and there's our set of initials E, which contain only nature's indeterminism. So x1, x2, y1, y2, not these choices, right? And then we can define the set of all transitions from any initial from this set E, right? You will recall my original writing a local possibility like this from some initial E to some local outcome of E. And so you take all of those. And then we provide a definition of when a set of instructions, so a set of these local transitions, when such a set is coherent, as we call it. And so this is a coherent set. It gives a unique instruction for as many initials as you can consistently do, right? So the important thing is the outcome prescribed for example, x1 is unique. So this is no blatant inconsistency, right? And whenever you can produce an experimental arrangement, it will give you a consistent prescription. So it will give you a prescription that accounts with the surface structure. So if there was a surface modal correlation, so for example an absence of, let's say, plus plus outcome, then no instruction set will prescribe this plus plus outcome. So, and then what we can do, this is the formal definition then, given all these instruction sets, we make copies of the whole structure which contains all these splittings, right? Such that at E star we enter all the instruction sets as different splittings now, and we copy everything above E star, and we delete the choices at the points from E, at nature's indeterminism, by sticking in, you know, what these instruction sets told you to do, and we're leaving the choice structure of these points intact. That's what it means, we think, to provide a non-contextual extension of a surface model. And the contextual one looks a bit differently. There the idea is you provide instructions for maximally consistent arrangements of initials for different contexts, for different situations that the experimenters together can arrange. And then for each of those, for as many of those as possible, in a way, this is this definition, you provide instructions. So you allow for one set of instructions in the context x1, x2, for example, to prescribe a value of x1 that is different from the value prescribed to x1 in the other context. And now this looks as if this should, so maybe you can think of situations, we will see one in a minute, you can think of situations in which this is going to be too narrow, too tight a constraint on the instruction sets, so you can't make this work. But this looks much broader because it allows you to put in an instruction set no matter what the experimenters will come up with, right? And so the idea would be that maybe the contextual hidden variables you can always introduce, fulfilling any constraint you might want to come up with. And now this all comes to grief for the GHC setup, and I'm handing over to Tomasz.
Thank you. So here is the GHZ experiment, and the idea is to apply the extension of BST models just to that very setup. So to repeat that, as I understand most of you know about it, there are those triples of particles produced by the source, and they go in separate directions into those boxes where the measurements take place. And while in flight, the experimenters there in the boxes have a choice of the setting. That's the polarization direction. So it's either X or Y here on that picture. And given the polarization direction is chosen, a result plus or minus appears. So there's that particular state that's flashed here that lived in the Hilbert space. And to say a few words about geometry, this X and Y, that's directions, the polarization direction. So X is in the direction perpendicular to the plane and flights, and Y, I is in the plane of flights. But well, to explain further this symbolism, we've got three layers of, two layers of choices. So here is this experimenters induced indeterminism, where each experimenter chooses one of the settings. So it's always X, Y, 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 and so on. And then, given the setting, the nature given indeterminism appears. So we got either plus or minus. So there are these two layers, and well, in line with the ideology, we want to keep the experimenter's choices intact while somehow reducing or modifying the choices provided by nature. That's not a BST model, it's just a prop for our memory. So one more thing about space-like relations. So each two choices, experimental's choices, are space-like related, and an experimental choice is space-like related to remote measurement setting. That's the second line. And measurement result in different stations that are also space-like related. So what is observed? These are triples, which are like here, x1 minus, y2 minus, y3 plus. And here quantum mechanics comes to the stage. Namely, it says about probabilities of these triples. And some triples have probability 0, which we read as inconsistent. They cannot happen in any history. So with this inconsistency instead of probability, here are these two rules, YY and XXX rule. The YY rule says triple with 2 Y's is consistent if even number of minuses, and triple with all 3 X's is consistent if odd number of minuses. Oh, so here is one history, an example of one history in a BST diagram. So the choices of experimenters are always X, X1, X2, X3, and the flashes, there are all 3 minus flashes. Now, given the quantum mechanical prescription, it's easy to note that some histories are missing. So for instance, the all pluses, that XXX plus 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 history, that's missing. And that shows modal funny business that Tomasz just explained, namely this intersection of histories, that's empty. So if we calculate the number of allowed histories given quantum mechanics, there would be 48 of them, and that's in contrast to 64, which are combinatorially possible. Well, so let's try to run the extensions procedure to this GHZ setup, and well, 2 constraints we assume. Namely, first, we modify choices given by nature. We try to leave experimenters' choices intact. As Tomasz just said, if the second thing is not assumed, so we are allowed to reduce experimenters' choices, the superdeterministic extension is possible. Okay, so it's always possible to do it superdeterministic. Now, what are the instruction sets? So, quite generally, we should have an instruction for any possible combination of settings. Okay, and the question mark indicates pluses and minuses that you are supposed to fill in. Now, if we are talking non-contextual instruction sets, that means that no matter what's the rest of x1 here, it should be the same. So x1 plus some rest, some other rest, the same x1 plus. Okay, so that means non-contextuality. The instruction, the very local instruction on x1, does not depend on the instruction given to the remaining 2. Okay, so that very fact that we have that independence allow us to rewrite this huge 8-element object into this very object, which consists just 6 entries, that is an entry for each possible setting. And our idea is, again, try to fill it in with pluses and minuses. Contextual instruction sets are different, so they allowed for dependence. You have here different rests, yeah, so x2, y3, y2, x3, and well, that somehow influences the first entry. So that's contextual, that depends on the context. So, well, to do the same the BST analysis on GHZ, here is the set of initials, that is the measurements from x1 to y3, and that produces the set of all possible or all locally possible transitions from x1 to plus and so on. And here we have a candidate for for a non-contextual instruction set, 6 entries, some pluses and minuses, and the question mark means here that we are in for trouble. There won't be any instruction sets of that sort. So that's really Mermin's argument in BST, which says there are no coherent 6-element subsets of that big tilde T, that is of the all transitions. So the argument really goes by, like in Mermin's paper. So recall the YY rule, that if you have 2 Ys, there must be even number of pluses for the triple to occur. So this very rule yields only those 8 possible instructions. There are no other possible instructions. And if you try to read from this instruction this one, x1, all x's and minus, which is okay. So it should occur somewhere. There is no way. Okay, so there is no x, y, x minus minus anywhere here. So that's really Mermin's argument in somewhat different setting. And here it says it's impossible to have an instruction set with 6 elements. But set theoretically, there must be those maximal coherent subset of our tilde T. That's just what set theory gives. So the question now is, what are these maximal coherent subsets of tilde T? And the argument here is that these are 5. So the punchline of that slide is that, well, there are those maximal coherent subset of tilde T. These are our instruction sets by definition. However, they are incomplete. They have 5 elements instead of 6. So there is some freedom in them. Okay? And how you produce these 5s? Well, the first observation is that you need either the form XX triple Y or triple XY. And starting with that form, the assignment of pluses and minuses to Y, there are 8 of them, determines the assignment to XX by the quantum rules. And then there are, as I said, there are 8 assignments of pluses and minuses to triple of Ys, and 3 choices of 2 X's out of 3 X's, so 24 total, symmetrically for the other form. So together we have 48. And finally, we note that coherent fourths are subset of difference 5s. So the punchline is there are 48 maximal coherent subsets. So, well, let's run the construction. Here are the just the 2 examples of these maximal coherent 5s. Okay. So let's take our example, that is this particular G. It's strange and it has no entry for Y3, and let's do the construction. So here's the diagram, and it indicates the 5 entries in this T. The red one here means they are missing in the instruction, but they are in the nature, okay? So now the question is, pick any history that passes through Y3, okay? And ask if it makes a good pair with T, okay? So, well, to make a good pair with T, these transitions should combine properly. So the requirement is that Y prime passing through Y3 makes a legitimate pair with T. If that's non-empty, then we've got this one. However, this particular transition is not in our set of T, because simply T is smaller. T is smaller, so these two red guys do not appear in T. So the punchline here is T and H prime are not any good. Okay, so that has an implication what the extension looks like. So if that's if that's a bundle of histories with a given T, we observe that that part here from Y3, it cannot have T assigned. So in the extended model, this part here is missing. So reading it informally, that means that the third experiment has no choice in that particular T bundle. Okay. So it's like a little local superdeterminism. Okay. In that particular bundle, the experimenter has no choice. You can improve on that in another T. So if you say if you take, for instance, this particular T1, then the experimenter, then there would be choice for the experimenter at 3. However, there would not be a choice at the first station. So the moral of that construction is that if you run non-contextual extension, then we remove locally experimenter's choice. Okay? So let's try to improve on that, and well, there is that larger framework of contextual instruction sets. So in that case, quite generally, an instruction set of that sort would have 8 triples, each providing an instruction in each different combination of setting. However, that freedom is somehow reduced by the fact that we have these 5-element maximal coherent subsets of our set tilde. So that means that given T, it fixes quite a number of gantries. So this particular T, since it has all data needed for X, as long as Y3 is not included, that fixes all these guys here. So we have X3 here instead of Y3. It's all fixed from that. The freedom is in this line. We cannot do anything about this one and the last one because our quantum rules doesn't say anything about it. However, the quantum rules are specific about this one because the YY rule apply. And the YY rule, if applied to these two, gives the verdict these 2 elements, Y prime and Y double prime, cannot be the same. They are different. So what we found out is that there is this locus for non-contextuality, namely these very guys here. The Y prime and Y double prime are different depending what's the rest here. So let me flash the slide explaining what is now happening with the extension. Now the instruction set is that 8, let's recall, that's this large object with 8 triples, and that T contains these 2 triples, okay? So these 2 guys that were absent earlier in the analysis of the non-contextual, they are in T. So if we ask the similar question, namely, well, how can we assign T to different elements here? The answer is you can assign T to both these arrow here, right and left, and everything here. You cannot assign t, however, here, as there is the other arrow, and so on. So what comes out as the result of the analysis is the following t-bundle. In t-bundle, you have in that determinism here, determinism here, determinism here, determinism here, determinism here, however, indeterminism there. Okay? So it's already strange, yeah, because somehow it works asymmetric. Why? At some measurement, the freedom is removed in another node. But it's actually even worse. The argument now is that MFB, which is the feature we wanted the whole construction to run, returns. So, well, the punchline, it's not of any use. So where the MFB returns, just looking back at these two instructions, yeah, we see that these triple of transitions are consistent. Okay. So we are looking C1, C2, and Y3. Okay. That's the initial. So two experimentals, one nature. Okay. So these two are okay. However, if we change the outcome part, this is not an option. That's forbidden. And that's exactly a case of model funny business. So you've got these three guys, C1, C2, Y3, well, it somehow disappeared. And, well, they are consistent. They live in one history. They are spatially related. However, some combination of their outcomes is impossible. Model funny business. And that's a catastrophe for the contextual construction because, well, it wanted to be general. It was more general than non-contextual. But the main reason was to remove model funny business. And all right, in one sense, the model funny business is removed from the experimenter's part. But, well, it comes back from the back door, so to speak, just by, well, producing a correlations between experimenter's decision and the choice at Y. So a recap on BST, and I'll be coming to the close. So first, this super deterministic extension that, well, removes freedom of both experimenters and indeterminism in nature. That's always possible. The extension with non-contextual instruction sets, that was the first construction, that removes freedom of some experimenters. So that has this, well, local super-deterministic aspect. And the third one, which we just done, that's with contextual instruction sets. And, well, that's very problematic because, well, it somehow makes the MF model funny business return. So, well, to give finally the conclusions of the talk. So in the BST framework that we somehow touched, but not really explained fully here, we can give a formal framework of model correlation and the model funny business. So in that treatment, we can make a distinction between non-contextual and contextual hidden variables, instruction sets. Okay. They provide different ways of extending the initial BST models, and that construction that brings a few novel aspects that at least were not so clearly formulated in the extant literature, namely it makes clear that distinction between nature-given indeterminism and indeterminism induced by agents. And then we have these new formulations of no-go theorems for GHC, namely non-contextual instructions introduce instances of less reduced or local superdeterminism. And finally, the contextual instruction sets do not remove model funny business. It basically moves model funny business from one place in the model to some other place. Thank you very much. And I just want to
So we'll take a very short break, a minute break, and then we'll have 25 minutes for questions.